Rivers on the surface of the Earth sustain life and nourish ecosystems. But too much or too little water can threaten those same environments and livelihoods.
An atmospheric river is essentially a river in the sky, but it's a river of water vapor rather than a liquid river like on land.
Atmospheric rivers are long, narrow, fast-moving, transient corridors of concentrated water vapor and wind that move horizontally in the lowest layers of the atmosphere.
An average atmospheric river moves about the equivalent of 25 Mississippi rivers worth of water at any given time. They're moving like 90 to 95% of all the water vapor. So they literally function as rivers in the sky.
Atmospheric rivers provide vital moisture for precipitation in many mid-latitude coastal regions around the world, such as California. Their moisture is derived from both tropical and mid-latitude sources. Pineapple Express is a term that was popularized in reference to one particular type of atmospheric river that stretches from near the Hawaiian Islands to the U.S. West Coast. We refer to all types of atmospheric rivers as ARs. ARs often stretch for more than 1,000 miles and are generally at least twice as long as they are wide. The highest concentration of water vapor is found in the lower atmosphere below 10,000 feet. When they interact with a mountain range or are lifted by atmospheric processes, ARs usually form clouds and result in precipitation. In addition to size and shape, they're also defined by the magnitude of moisture transport as defined by a numerical measure called integrated vapor transport, or IVT. IVT represents the combined effect of winds and moisture and can illustrate the horizontal movement of water vapor through the atmosphere. ARs are generally defined as having an IVT threshold greater than 250 kilograms of water vapor per meter per second. Of course, the IVT value can be much greater. Most ARs are beneficial and are critical for recharging water supplies. Others can cause extreme precipitation, leading to hazards like floods and landslides. Burn areas can be particularly sensitive to intense rainfall.
I'm standing in an area in the coastal mountains of Northern California that burned in a wildfire. Along the U.S. West Coast, summer and autumn wildfires are followed by the wet season, and in the wet season, atmospheric rivers can bring high-intensity rainfall that can cause flash flooding and debris flows on burn areas.
Conversely, a lack of significant atmospheric river activity can lead to water shortages and drought.
Atmospheric rivers are a natural part of what are called extratropical cyclones.
When extratropical cyclones draw together moisture and accelerate the wind, they bring together these two elements needed to form atmospheric rivers. Atmospheric river climatology shows that they occur most frequently in the mid-latitude oceans. Over the North Pacific, they typically have a southwest to northeast orientation. Although they occur throughout the water year, ARs along the west coast are more common in the cooler season. In California, the highest monthly precipitation typically occurs November through April. In many mid-latitude coastal areas around the world, such as the west coast of North America, the amount of moisture transported by ARs contributes to a significant portion of the total annual precipitation.
Here in California in particular, some places get about half of the annual precipitation in just a few atmospheric river storms each year. The Sierra Nevada of California typically gets about 40% of its average snowpack from atmospheric river storms.
While ARs are important for replenishing annual water reserves, there can be wide variability from year to year. These climate stations have shown the greatest year-to-year variability in precipitation. California, and especially Southern California, has the greatest variability, making long-range planning challenging.
In California, it's plus or minus 50% in large areas of the state. So it can go from 20 inches to 60 inches from year to year, which makes for very special needs for managing water and flood and providing for ability to get through a drought. So the Center for Western Weather and Water Extremes, or CW3E for short, is something I founded here at Scripps Institution of Oceanography in 2013, specifically to address problems in the West with extremes in water and the weather that produces it. Atmospheric rivers are the primary driver of extremes in water in the West, and hence it's been a major focus of our center's development.
The CW3E website provides access to observations from the surface, from satellites, and from reconnaissance flights over the ocean.
Atmospheric river reconnaissance observations provide detailed vertical profiles of key parameters like temperature, wind, moisture, and pressure. Surface observations provide critical real-time data once the event is happening. This supports water management decisions and warnings about localized hazards like flash floods and debris flows.
Surface-based observations of ARs include snow-level radar, profilers, and integrated water vapor measurements.
Observations of atmospheric rivers help us determine how they will interact with the mountains. This is a key contributing factor to determining whether they will penetrate well inland or deposit most of their moisture near the coast.
CW3E provides detailed forecasts out to 7 days for IVT, as well as for integrated water vapor, IWV. Numerous other model-based products, both deterministic and probabilistic, focus on the prediction of ARs. The AR landfall tool illustrates the probability of specific IVT thresholds for a comprehensive set of forecast points along and just inland from the coast. This provides for lead times out to 16 days, improving situational awareness of the probability, duration, location, and timing of landfalling ARs. The AR scale consists of 5 rankings that are determined at specific locations based on the expected duration of AR conditions and maximum IVT. Higher IVT magnitudes and longer duration ARs rank higher on the scale. AR1s are weak and tend to have primarily beneficial impacts. AR5s are primarily hazardous, with both great strength and prolonged duration, resulting in extreme precipitation. Forecast-Informed Reservoir Operations, or FIRO, provides a way for water managers to better plan for the spectrum of AR benefits to AR hazards and to make the water supply more resilient in the face of climate variability and change.
FIRO manages 2 important risks. It manages the risk of a dwindling water supply by allowing for more storage during forecasted drought conditions. It also manages the risk of downstream flooding by allowing for more water releases prior to a forecasted significant storm.
FIRO gives water managers and reservoir operators actionable information based on real-time AR forecasts. As climate change continues, models suggest a wider season-to-season variability. ARs are projected to play an increasing role in extreme weather and climate events, ranging from droughts to floods.
So literally the future of climate in terms of overall annual precipitation, wet or dry, is going to hinge in this part of the world heavily on the fate of atmospheric rivers in a changing climate.
The tools available on the CW3E site at Scripps Institution of Oceanography, UC San Diego, help us to anticipate the impacts of atmospheric rivers, now and in an uncertain future.